The most basic arithmetic operation is succession. Succession is just adding 1 to a number. The level above is addition. Addition is repeated succession. A plus b is equal to adding 1 to a b times. Then we have multiplication. Multiplication is repeated addition. A times b is equal to adding a to itself b times. Level above multiplication is exponentiation. Exponentiation is repeated multiplication. A to the power of b is equal to a multiplied by itself b times. The next operation probably many people didn't hear about. Tetration. Tetration is repeated exponentiation. A tetrated to b is equal to a raised to the power of itself b times. In other words, it is a tower of exponents with the height of b. Tetration is a very powerful operation that can generate incredibly large numbers. For example, 3 tetrated to 4 is a tower of 4 threes. To evaluate the tetration, we always start from the top. So 3 to the power of 3 is 27. 3 to the power of 27 is already equal to more than 7 trillion. Multiplying 3 by itself this many times results in a gigantic number. This number has over 3 trillion digits. With just the numbers 3 and 4, tetration can create numbers that are so enormous that it's hard for us even to imagine them. But tetration doesn't always have to generate numbers this big. 1 tetrated to any number is always a 1. Even if we have an infinite tower of 1s, it's still just 1. This is a trivial example, but now consider an infinite tower of square roots of 2. We can write it as the square root of 2 tetrated to infinity. But a more accurate way to express it would be using a limit as x approaches infinity of the square root of 2 tetrated to x. Surprisingly, this infinite tower converges to 2. The limit exists when we tetrate a number that's between e to the power of minus e and e to the power of 1 over e, which is an interval from around 0.07 to 1.44. The square root of 2 falls within this range. So far, we have written tetration using the left exponent. Unfortunately, there is no standard notation for tetration, but 2 up arrows are used very often, and this notation will allow us to express even higher level operations beyond tetration. The arrow notation can be also used to write exponentiation. A to the power of b can be written as a up arrow b. With this notation, we can define an operation on level 5. Using 3 arrows, we denote pentation. Just like tetration is repeated exponentiation, pentation is repeated tetration. A pentated to b is equal to a tetrated to itself b times. 3 pentated to 3 is equal to 3 tetrated to 3 tetrated to 3. And 3 tetrated to 3 is equal to 3 to the power of 3 to the power of 3. And that is equal to more than 7 trillion. And 3 tetrated to this number is a tower of 3s of height more than 7 trillion. This number is unimaginably massive. But we can go a level higher. With 4 arrows we can denote hexation. Hexation is repeated pentation. 3 hexated to 3 is equal to 3 pentated to 3 pentated to 3. This number can't be compared to anything in the real world. With this giant number, we can start creating the Graham's number, which is one of the most famous big numbers. To construct it, we start by defining that 3 hexated to 3 is equal to G0. Hexation is denoted using only 4 arrows and already generates enormous numbers, but G1 is equal to 3 followed by G0 number of arrows and another 3. Just imagine how big this number is. Next we have G2, which is denoted using G1 number of arrows. G3 is equal to 3, G2 number of arrows and 3. This sequence continues until we get to the G63, which is equal to 3 followed by G62 arrows and 3. That is the Graham's number. Graham's number was used by Ronald Graham as a simplified explanation of the upper bounds of the problem he was working on. At the time of its introduction, it was the largest specific positive integer ever to have been used in a published mathematical proof. In 1980, Graham's number was described in the Guinness Book of World Records. Since then, many bigger numbers have appeared in mathematical proofs. For example, the Graham's number is extremely small in comparison to the tree of 3. To explain what this number is, we need to play a game of trees. In this game, we try to create a forest using colored seeds. following two rules. The nth tree can't have more than n seeds. The first tree can have only one seed, the next can have more than two, and so on. The second rule is that when you try to build a tree, it cannot contain any of the earlier trees within itself. For example, this tree contains this one, so it cannot be built. Also, the tree is contained in another tree when they preserve the nearest common ancestor rule. In this tree, the nearest common ancestor of the yellow and red seeds is the green seed. In the other tree, the nearest common ancestor of the yellow and red seeds is also the green seed. It means that the first tree is contained in the second tree, so the second tree cannot be built. The tree of n function tells us how many trees we can build using n colors of seeds. Using one color, we can only build one tree, because the first tree will have one seed, and any further trees would contain this tree. So tree of 1 is equal to 1. When we have two colors of seeds, red and green, the first tree has one red seed, the next can have any red seeds because it would contain the first tree, so we can use two green seeds. To build the next tree, we still can't use the red seeds, we also can't use more than two green seeds. But the third tree can have at most 3 seeds, so it can have only one seed, and it can only be a green seed to not contain any of the previous trees. We can't build any more trees, so tree of 2 is equal to 3. Using 3 colors of seeds, we start with a tree that has only one seed. Then we can have this tree, then another one, and all of them obey the rules of the game. And we can go on, and build more and more trees. The total number of trees we can build using 3 colors of seeds is equal to tree of 3. This number is massive even when compared to Graham's number, but we know that it is finite. Graham's number, denoted as G63, is a colossal number, but we don't have to stop at G63. We can keep going. G64 is defined as 3 followed by G63 arrows and another 3. We can even create numbers like G100, G1000, or even G1 million. But none of them would even come close to the tree of 3. We know that tree of 3 is a lot bigger than G3 followed by this many arrows and another 3. The tree function generates incredibly massive numbers. Tree of 4 is already a lot bigger than tree of 3. We can put any number into the tree function. Just imagine how big would be tree of Graham's number, or tree of 3, or tree of Graham's number. These numbers are beyond our comprehension in terms of size.